This video is going to look at behaviour and speed of response given a Laplace transform, and in particular it's a tutorial sheet. The idea is that we're going to provide a few tutorial or exam style questions on speed of response and behaviours. Students should pause the video, having read the question, attempt the questions, and only look at the solutions once they've had a proper go by themselves. A little bit of a reminder of the background. This is of course covered in other videos, so it's just a reminder that if you look at pole positions in the complex plane, you can very easily identify poles that are far into the left half plane tend to have associated with fast convergence, poles that are close to the imaginary axis, slow convergence, poles with large imaginary parts associated with oscillation, and poles in the right half plane are associated with divergence. Here's the question then. So you'll see we've given 6 Laplace transforms, and what we want you to do is categorize this into which is the fastest expected behavior, which is the slowest, and so on. Now, a reminder, you should pause the video at this point while you do this categorization and say what you expect before you go on and look at the solution. Here's our solution then. We'll do each transfer form one at a time. First of all, f of s is 2 over s plus 5. This has got a pole at minus 5, which we would expect to be moderately fast. The next one has got poles at plus or minus 2j, which means we expect oscillation, or I could say pure oscillation, no convergence. So in fact, I'm going to cross this one from the analysis because it doesn't converge at all, so we can't really talk about speed of response. The next one's got poles at minus 2 and minus 4. So this is fast, or reasonably fast, but it's not as fast as the one above. So I'm going to put here faster for the one above and fast for h of s. This next one has got poles at minus a half plus or minus j root 3.5. A bit of a messy one there, and the key thing is you can see that this one is on the slow side because the real part of the poles are minus a half, and therefore it's not going to be as fast as the two above, whose poles are further into the left half plane. The next one has got poles at minus 0.2, minus 0.2 and 0, so this one's going to be even slower because the poles are moving closer to the imaginary axis. And the final one at the bottom has got poles at minus 3, plus or minus j, and minus 1. So this is the middle. You'll see it's faster than the two we've marked as slow, but not quite as fast as the one we've marked as fast because it's got this pole here at minus 1. Now that we've written down what we expect to happen, you remember that we often say, well, good thing to do is put the transfer functions into MATLAB and see what you get there, because if you get the same thing out of MATLAB as you got on pen and paper, then that validates your understanding and you're a lot more confident. However, we have given you a warning here. Remember that if a system's got lots of poles, you can't always tell how big the residue will be for a particular pole position. So just because it has what appears to be a very slow pole doesn't mean it will necessarily have very slow convergence, because that pole may have a negligible residue. However, I wouldn't worry about that in general, because what we're looking at is expectations. Let's go to MATLAB now then. You'll see what we've done here in this highlighted code. We've defined all our transfer functions. So I'll dump that across. So there we are, we've entered all the transfer functions that were given in this question set. And now what we're going to do is do the numeric inverse Laplace, that's what this impulse statement does, and plot them all on a figure and see what we get. So let's just move to the figure. There it is. And what do you notice? F is in blue. you'll see the blue curve down here, and we expected that to be the fastest, and indeed you can see of all our signals that one has converged the fastest. G was the sinusoid, which oscillated forever, and again you can see this green curve going up and down, and it's not converging, and we had said ignore that. H, I can't remember which one that was, but we can check in a minute. I think H had the -2 and -4. We said that should converge fairly fast, but not as fast as the blue, and again you can see in this red curve it converges fairly fast, but not as fast as the blue. M had some relatively slow poles, and therefore we expected it to converge pretty slowly and to oscillate at the same time, and what do you see? Here it is, it's oscillating up and down and converging relatively slowly. N had the integrator, and therefore wasn't converging to 0 at all, was converging somewhere else, and you can see that's what we're observing here. And finally, K was, you'll remember it had a pole at -3 and a pole at -1, and so was that faster or slower than the red? And you'll see actually they're fairly similar. They've got different magnitudes, so that disguises the fact a bit, but they converge at about the same rate, which is roughly what you expected. So the next question set. This question set is more focused on behaviour, so not just speed of response, but behaviour. What sort of behaviour do we expect? So again, I'm going to suggest you press pause before we continue, but just to mark something in case you don't notice, while all these transfer functions seem to be the same, this one is different. It's slightly different from on the previous set of examples, so just make sure you notice that. I'm going to continue now. Okay, so this one here, we had a simple exponential. So what we could do is we could draw a happy face. Yeah, it's converged quite fast. It's a simple exponential. We're quite happy with this. This one, you remember, we said it was oscillation. So generally, that's not particularly good. This one here, which we marked as being different, what you should notice is this S-4. It's unstable or divergent. So that's bad news. This one here had poles at -0.5 plus or minus j root 3.5, and so what you expect is the oscillation dominates, okay, the decay. So that's going to have bad behaviour because you've got quite a high frequency of oscillation compared to the speed at which it decays. This one here, you'll notice I've got an s², so this will actually be divergent. It will go off to infinity because I've got a double pole at the origin. So again, I won't be able to plot that one. And this one here, you had poles at -1 and -3 plus or minus j, so you should have decay dominates the oscillation. So this one you expect to be satisfactory. So we've given here on this page what we expect to see. So what are we going to do next? Again, we're going to go to MATLAB and look at the examples and say, did I get what I expected? So I'm not going to redo the transfer functions. What I'm going to do is I'm going to do step responses this time, just for a change, and look and see what do I get. So you'll notice the same thing that we mentioned before. The green curve was the cosine, and you can see it oscillates up and down and goes all over the place. You're not particularly happy with that, and that's what we said. The dark blue curve corresponds to f, converges nicely, converges smoothly. You're very happy. The cyan curve corresponds to k, where we said we did have an oscillatory part, but the decay would dominate the oscillation, and that's what you can see. It still seems to behave quite nicely. Whereas the red curve corresponds to the position where the oscillation dominated the decay, and that's what you can see here. So the key point is that using MATLAB we're able to consolidate or reinforce what we expected to happen, and that makes us more confident. So in conclusion, we've given a short tutorial sheet on behaviour and speed of response, and we've demonstrated the use of MATLAB for checking your expectations. And what you need to do now is create a number of Laplace transforms of your own, have a look at them, decide what you expect, and then use MATLAB to overlay the actual responses to check, Does it do what you expect? And if it does, you've got it.